Okay, let's go ahead and get started for today. We're going to be resuming our discussion of MRI today after a pause for the projects. So before we start in with the lecture material, are there any questions about course logistics or anything related to the course in terms of material or where we're going? Anything in the class? No? Yes, question.
Participation quizzes can be for every lecture.
The pre-lecture quizzes?
The pre-lecture quizzes.
Yeah, I'll try to have a few for every lecture. I mean, they're meant to be fairly easy. Just if you watched it, then it should be, yeah. So that's the idea, to help you. And that way, if it helps me, because if there is a question that's where a lot of people don't get it, then that will help me. And then typically what we'll do is throughout the next lecture, then I will weave the answers in to the lecture, to the answers. So that basically is how it works. Okay, sure. Any questions from the video world? Let me make sure I have my chat up. Where'd my chat go? There it is. Okay, all right, so today, oh yes, question.
Can the ones for the entire week be still?
Sorry, can you say it again?
The quizzes for like both lectures of the week be the after?
Oh, I see. Yeah, they could, although I'm not always sure what I'm going to cover in a given lecture. So typically what will happen is within an hour or two of, yeah, the shortest is always between Monday and Tuesday, right? But I don't know what I'm going to cover, how much I'm going to get through on Monday. So typically just expect by like that afternoon, it will be posted. Yeah, so yeah. So in general, then, yeah, I mean, the Monday ones will be a little easier probably than the Wednesday ones, simply because you have less time to review it. But they're not meant to be hard. They're just meant to be like, did you know what left and right is? Things like that. Okay. All right. Any other questions? And also the grading is very, as you see, very sort of participation based. Like if you do nothing, you still get like 7 points. Okay. Great. So if there's no other questions about logistics, let's get started with today's lecture material. So we are going to resume our discussion of MRI. These are the topics I'd like to try to get through. Hour of excitation, we're going to review that and do some new material. We'll look at, basically today, we're really going to start getting into sort of the physics of MRI, just enough physics so that you can understand how we make an image. Okay, so MRI is sort of, there's a bunch of physics you need to understand, just the bare minimum to get you started. And then once we have that machinery, then we're going to actually switch gears a little bit and talk about how do you make images. Okay, and that'll tend to be a little more sort of image reconstruction. We're going to do Fourier sort of reconstruction, but also given the fact that the way reconstruction has evolved over the last decade or two, especially with deep learning now, it's actually much more effective and more useful for all of you to actually have a more linear algebraic understanding of image reconstruction, because the Fourier is very useful and it's good to have, and you should always start off with that as your sort of, that's the basis, but really modern reconstruction goes beyond Fourier. Okay, so 20 years ago, this was all just Fourier. Okay, now it cannot just be Fourier because most reconstruction now is not Fourier. Okay, but Fourier is the starting point. Okay, so we'll talk a little bit about what are the transverse and longitudinal components. We'll talk about relaxation, block equation, and hopefully get through K-space review. I'm not sure we'll get to encoding with gradient term or signal equation today, but we'll see how far we get. Okay. Okay, so just to remind you, what we spent most of last time talking about was the role of this magnet, right? And I think one of the questions on the quiz was, what is the role of this magnet? And it's polarization, right? Basically, it's just to create some magnetization that you can work with, because if you don't have a external B field, then the spins are randomly oriented, and so their magnetic moments are randomly oriented. There's no net magnetization for you to work with. Right? So we need this external field, and the stronger the field, the more polarization we have. And so that's one of the pushes. So there's two ways to address the problem. One is you can just build bigger and bigger magnets, right? But that's like $1 million per Tesla just for the magnet, plus probably 500,000 per Tesla for the sighting, because these get heavier and heavier, right? So the other extreme is saying, well, actually, why don't we go the other way? Let's go to lower field. We have less signal, but let's use deep learning and other tricks to sort of get around that. Okay, so there's two ways of going around the problem. And obviously in the middle, there's no reason you can't apply deep learning to things in the, 3 Tesla or 4 Tesla. It's just that the gains tend to be less, right? If you go to low field, you really need deep learning to help make up the fact that you don't have any signal. If you have enough signal, it helps. Maybe it helps go faster, we'll see later, but it's not as critical. You can still do the job without deep learning, right? Which has been done for the last 30 or 40 years. Okay, so that was what we talked about. And the other thing we talked about that's sort of important is, and we'll revisit this in a minute, is precession. That the other thing that spins do is, in the presence of an external magnetic field, spins will tend to precess around that magnetic field. Okay, so that actually, the precession aspect actually turns out to be super important for almost all aspects of MRI. We'll see it in excitation, we'll see it in encoding. And so you'll want to sort of get a good handle on what precession looks like, and we'll have lots of examples of that. What we're going to talk about now for most of today is excitation, or at least for the first half of this lecture, which is essentially, now that I've created this magnetization, so the big magnet creates this polarization, so I have energy to work with. But it's really, let's say I have different magnetization at different points in my object, right? It's like I have little different bar magnets of different strength, right? And I want to sense it from out here, okay? It's basically, it's sort of like if I had a bunch of magnets in a bag at different strengths, and you're just trying to measure the magnetic field out here, it's really hard for me to tell what those magnets are, right? Because you just get the sum of all those magnets, right? They don't really have any spatial information. And it's really hard to get that. So it turns out that if I can make each one of those magnets spin around, right now, each of them is like a little antenna. And if I can get them, and what we're going to is if I can get them to spin at different frequencies, now they're basically little radio stations transmitting at different frequencies. And then I can listen to it out here. Okay, so that's why we excite the magnetization. We want to take it away from just being this little bar magnet to being a magnet that is going to precess around and now can sort of broadcast its location and magnitude to us. Right? So that's why we do excitation. Now, the encoding part we just sort of alluded to. The encoding part is making each of those magnets spin at a different rate. Okay, so it's sort of like on your radio, you've got different radio stations. So essentially each magnet, depending on its location, is like a different radio station broadcasting its different frequency. Okay, that's the simplest picture. Now, to get to 2D imaging and 3D imaging, it's sort of, we have to make that a little more sophisticated, and that's when we're going to go into K-space and K-space trajectories. And finally, what we'll get to, as we talked about last time, is what we're heading towards is once we've done all that, then we want to sort of listen to the signal. Okay, and so we're out here listening to the signal, and that process of listening you can consider integration, because it's basically listening to the signal from all the different parts of an object. Okay, so that's essentially integrating my signal over the entire object. Right? So that's, once again, a review of where we're headed. And so today we'll mostly focus on excitation and hopefully get into encoding as well. Okay, so just to remind you, the most important part is that there's really 2 precessions going on. There's precession around the B0 field, and that's sort of, we always assume that's happening. That occurs at omega equals gamma B0. Okay, where this is the gyromagnetic ratio. And this is the main field. Okay, and this is in radians per second. Okay, so this is essentially what we call the Larmor frequency. Okay, and so that's super important. So basically everything depends on a spin's Larmor frequency. And so in terms of hertz per cycles per second, which is hertz, we can write it as gamma over 2 pi B0. Okay. And so it's, for most people, and including myself, I find it sort of a little easier to think in terms of cycles per second or hertz, because that's what we talk about when we talk about radio stations and everything. It's sort of, everything's in hertz. Okay. So typically a good thing to remember is gamma over 2 pi for hydrogen proton is roughly 4257 hertz per Gauss, or sometimes 4258 depending on how you ask. But it's sort of, those are sort of the good numbers to, so anyone who does MR sort of has these numbers in the back of their head, okay? Or else it's 42.57 megahertz per Tesla. Okay, now you don't actually have to remember this for this course, but if you end up doing MRI, these are just good numbers to have in the back of your head. So what that means is, for example, here, sitting here in this room in San Diego, maybe the Earth's magnetic field is about half a Gauss, right? So I think those of you has anyone measured the fields? You all did that already, right? Okay, you already measured the fields, and so you know it's about half a Gauss, all right? And so the frequency of your protons as you're sitting in this room is roughly 2000 hertz, right? So you don't feel anything, but actually all the protons in your body are somewhat aligned with the BE280 field right now, and they're all processing around, okay? And in fact, people have tried to use this for things like, I don't know where in Russia it was, maybe in Siberia, but they would try to use the natural resonance frequency of oil and look for oil deposits. And so they would build this big loop, just wire, maybe, I don't know, a kilometer in diameter or something, just to try to measure, and see if they can find out where oil was. I don't know, remember how successful it was, but that is possible to do. You could do Earth field MRI. Okay. So that's the main field, the BE280 field. Okay, so that creates, remember, polarization, and there's also precession around that field. Okay. The second field, which we're going to talk about today, is the BE1 field. Okay. And this is essentially what we talked about last time, where we have the analogy of you had your friend on a merry-go-round, right? That precession around the merry-go-round, that's like the main precession. That's like your Larmor frequency. Okay. And your job is to have a very, and obviously to make the merry-go-round requires a lot of energy, right? That's the main field, right? That's like, that's a huge amount of energy to do that. And then your job, the analogy of the job of the BE1 field is you come with a little, a thread, and you need to pull that magnetization, tip it away from its steady state away. And the only way you have a chance of doing that is you've got to run along. Okay. And it's essentially the same thing. We're going to have a very strong BE280 field, right? And the precession spins are going to want to precess around this way. So it's always going to be a clockwise precession if we're looking down, okay? And so we have this BE1 field, and it has to go along the same frequency as that precession, because essentially if it does that, then it can sort of tip this magnetization away, okay? Because spins will also want to precess around this field, okay? Spins want to precess around any field, and it's just if this is the right frequency, then it will tend to precess away, and it will go like that, okay? All right. So that's shown in this picture here. We have our net magnetization. Everything is precessing around BE280. And now we apply this BE1, and we start to see the whole sort of net magnetization tipping away. Okay. And it turns out we can tip it to any angle we want. So there's like 90-degree flip angle. There we've tipped it 180 degrees away. And we can keep, if we keep adding energy, it'll overflip and go to sort of beyond 180 degrees back to, like, now it's 270 degrees, which is the same as 90 degrees. And so that's what we're doing with the magnetization. Okay, and so that angle which we flipped it is called the flip angle, okay, which we'll talk about in detail. Okay. And in fact, when you go to an MRI console, that's one of the parameters you set. You set the flip angle. Okay. And we'll talk about that later on how you would set that. Okay, so just to remind you, this is just another way of looking at it. So in the red, you're going to see the magnetization. And in the blue, you're going to see the BE1 field. Okay. And you see, if we're on resonance, then we are able to tip that magnetization away and spiral it down. And for most things, the easiest thing is we assume we're just going to do a 90-degree flip angle. So that there is a 90-degree flip angle. We just tipped it 90 degrees. Okay. And then if we are not at the right resonance, then it's sort of like you're running along at the wrong speed, along that merry-go-round, and your force is just not useful, right? And in fact, if you tug too hard, the string is going to break. All right, so that's sort of mentally a sort of analogy that you can keep in mind. Okay, now it's sort of, yes, question.
Is the normal frequency the same as the angular frequency of the spin?
No, it's different from the angular momentum of the spin.
Not momentum, the angular speed.
Yes, the normal frequency, right? If it's omega equals gamma b is the angular frequency.
Of the spin.
Yes, of the spin. Yes. Yeah. Now, this is where, it's very hard to talk about any one spin. Although now, actually, you can start manipulating individual spins, right? I mean, it's actually possible, which is pretty amazing. But generally in MRI, we never talk about one individual spin, at least for the MRI we're doing here. We're always talking about a sort of a collection of spins. And so it's the net magnetization that we think about, its frequency. Okay. But yeah, if you're sort of doing really high-end physics, you can actually go now and actually manipulate one spin at a time, which is pretty amazing. Okay. So for example, quantum computing. Right. Okay, so it's actually sort of, if you have to keep track of this thing going around, it's sort of quite confusing and it makes the math hard. So we are going to use what's called a rotating frame of reference for most of this class, or from now on, we're going to use a rotating frame of reference. Essentially, this is sort of referencing everything to the magnetic field at the isocenter. Okay, so the analogy would be, instead of you standing on the ground watching your friend spin around a merry-go-round, you're going to hop onto the merry-go-round. Okay, and so in that frame of reference, your friend is not moving around like this. And in that frame of reference, they're just falling right towards you. Okay, so you don't have to worry about this sort of spiraling around. All right. And I think we're all used to that because we're all right now on a rotating frame of reference. We're spinning around. I don't know how fast we're spinning around on the Earth, but we don't really worry about it. We just worry about the relative relationship on this spinning frame of reference. Okay, so what that means is we can go from what's called the laboratory frame to the rotating frame. Okay, so remember in the laboratory frame, we had to worry about this spiraling down in the magnetization. Okay, in the rotating frame, it's much simpler. This is the picture in the rotating frame. It's just basically spinning around. Okay, so that's the main picture, that we can just assume that it's just processing. Essentially, the precession is just around this B1 field. In that rotating frame of reference. Oops, just a minute. Okay, so now we're going to talk about the flip angle. And the flip angle is simply how much we've tipped that magnetization away from its the equilibrium position, which is aligned with Z. And the simplest picture is here. If we consider we're in the rotating frame here, okay, then we're just assuming precession around the B1 field. Okay? And we know how to write precession. This is just precessing at some omega1 equals gamma times B1. Okay? So essentially in the rotating frame, it turns out we can just ignore the B0 field, because essentially we're going at the same rate as the B0 field, so we can sort of ignore its influence. Okay? So in the rotating frame, all we have to worry about is that B1 field, right? And so we know that its angular precession frequency is just gamma times B1, and therefore we can write the flip angle as the integral of that over time. So let's take a very simple example. This is what's called a hard pulse. Okay, so the pulse would look like this. In time, I would just turn on my B1 field and have it on for 400 microseconds. Okay. And the question is simply, if I want a theta of pi over 2, what should this amplitude be? So this is the first calculation we're going to do with MRI. I think there's one of these similar on the homework 5. Okay, so with this, you should be able to do that homework 5 problem. So we know that the area of this, right? So it says we just want the area, we want the area of gamma B1 to equal pi over 2, right? And since it's a square wave, let's call this tau, all right? That's just gamma B1 times tau equals pi over 2. And so we just solve for B1 equals pi over 2 over gamma times tau. All right, and then we just plug in the values. So one thing just to keep in mind is typically, like as it is, I typically remember what this is gamma over 2 pi is equal to 4257 hertz per Gauss. That's just an easy number to remember. And so then anywhere you need gamma, you just multiply it by this 2 pi. Okay, so just remember one number and then you can always multiply by 2 pi later. And the nice thing is typically pi's cancel out, so that's nice too. So we put in our flip angle, pi over 2, we put in our gyrometry ratio, gamma, we put in our tau, 400 microseconds, and with that, we end up with 0.1468 Gauss as our answer. So the good thing is a lot of the stuff we do in this class is the algebra, the math is just super simple, okay? As long as you use the right formulas, right? So in your homework, I think you're asked to look at a more complicated pulse, which is sort of like a sync pulse, right? And there you don't want to necessarily be integrating a sync to find its area, but that's where you use Fourier transform to say, well, I know I have a very easy expression for what the area of a sync pulse is. And so you would use the area of the sync pulse. Okay, so let's, oh, in fact, this is it. Consider an RF pulse of the form, let's see, oh, good, all right. So actually, yeah, let's do this. So let's go ahead and sort of assign this as an in-class problem to do. And so go ahead and let's take a minute or two or a few minutes to do this one. So go ahead and you can talk to your neighbors and sort of discuss this. And I'm going to open up the poll. Those of you online can do this. And even if you're in the class, if you want to log on to Zoom, that's fine. Otherwise, we'll just sort of do an audio poll. Okay. So feel free to talk to your neighbors and take a look at this. Okay. Okay, about another minute, and then we'll sort of see what people think. Okay, we've got people online. So in class, just at the count of three, just sort of say out what you think your answer is, and we'll just sort of do a weighted audio poll. Okay. So on the count of three, 1, 2, 3. Okay, great. So I hear F as the main answer. Online, it looks like F is the leader at 35%, followed by a range of B, C, D, E, and G. Okay. So yeah, so that's great. So let's go through this. And the good news is if we go through this and you understand the answer, that problem on the homework should be pretty easy. Okay. So let's look at this. So the key is I have this sync function, right? And it has an amplitude of A, and the first 0 is at T. Okay, so very good thing to remember is that the sync of integer values is always 0. So you always want to just think about where's the first 0 of my sync function. All right. So I want to know the area of, in general, I want to know what is the area of this, right? And I know that the area of sync T of T, okay, is just the Fourier, it's a Fourier transform at F equals 0, let's say. Okay, so it's a Fourier transform of this thing. Okay, so the Fourier transform of this guy is F times rect Ft, right? That's its Fourier transform by the scaling theorem. Okay, then I just plug in F equals 0, and I get it's just T. Okay. So the nice thing is I know the area of this is just A times T, right? Okay. And I know that I'm just trying to get gamma times A times T equals pi over 4. Yes?
Why is it at F equals 0?
That's on your homework to prove. Yes, question.
How do you use the Parseval's theorem?
Sorry, can you say that again?
Parseval.
Parseval's theorem?
Fourier sine.
Well, Parseval's theorem is actually the sum of the squares. So that's energy. We're just looking at area here. So you would not want to use Parseval's theorem for this. Yeah, that's a good question though. I mean, Parseval's theorem is very useful for a lot of things, but in this case, you just want to use the fact that the area of any function is just the value of its Fourier transform at 0. That turns out to be very important also for imaging, because that means that in MRI, we acquire data in a Fourier transform. So the meaning of the center of K space is essentially the average of your object. Okay, and that's why that value tends to be very bright, because most objects we look at have non-zero area. Okay. Any other questions? That's a good question. Okay. Okay, so we have this. So now we can just say, so we can just solve for A, right? We just say A equals pi over 4 divided by, let's see, there's a 4 here. Wait, we have the pi over 4 there already. So we have T is 250 microseconds, right? And we will have gamma, so that's 2 pi times 4,000. We're just told to use 4,000 here, right? Okay, so the pi's divide out, right? And then I get, let's see, 1 over, what is that? It's like, this is gonna be 1,000, 250 times 4 is 1,000. So that's 10 to the 3. So 10 to the 3 times 10 to the minus 6 is 10 to the minus 3, right? Times 4,000, right? Make sure I'm doing my math correctly here. Times a 2, right? So that just equals 1/8 equals 0.125 Gauss. And the closest answer then is the 0.12 Gauss. Okay, so that's essentially what you're going to do for that one homework problem. Something similar. So if there's any questions, let me know. Okay. Oh yeah, so this isn't, I know this looks scary, but we'll walk through it, so don't worry about it. So just to remind you how we mathematically describe precession, because we want to work our way up to what's called the Bloch equation, which is the governing equation for MRI or NMR in general. This is basically the equations of motion for magnetization. Okay. So the first thing is I just want to remind you that this is essentially what does free precession. This thing where we're going to take basically M cross B, right? That's the main thing. So M is the magnetization. We're crossing it with the magnetic field. Remember from high school that anytime you do a cross product, it's the right-hand rule. So M cross B is going to give you a vector that, and that vector is your dm dt, which is going to give you this rotation. Now, you may or may not remember that the way to describe the cross product is just as a determinant of this thing, where you take the ijk, the mx, my, mz, and the dx, dy, dz. Okay, so that's something you may or may not remember. And then also you may or may not remember how to evaluate the determinant. Okay, but basically you just take I hat and then this mbx dz minus that, and so on and so forth. So you don't have to worry about this. This is just showing you this is where it comes from. That basically we just want to write something in a cross product in terms of a matrix algebra formulation, because that's how we're going to describe our system. Okay, so it just turns out that you can write that as on the left side, you've got your dmx dt, dmy dt, dmz dt. And then this is for a static field. So we're assuming that all we have is B naught. Okay, we haven't applied the B1 yet. And it turns out that this is the equation of motion. Okay, and so this is the equation of motion that gives you free precession. All it does is just do that. Okay, given any m, it just makes the magnetization go like that. So that's all you need to remember, that's what that equation is trying to tell you to do. Okay. Now in this case, actually we've left it in fairly general form so that we've actually let you have bx and bx components. But if it's just a b equals b0, we just assume that's typically b naught equals z hat. And so these terms would go away, right? And then all you have is this thing, okay? And so as you can sort of see, that means that dmz dt equals 0 for free precession. So that means that this thing just goes around the xy axis. Okay. So now we need to review phasors, and I think we saw a little of this in one of the Professor McVeigh's lecture. We probably saw a similar slide. Now we just want to remind you, because phasors, understanding phasors is essential to MRI. Okay. So just to remind you, we're going to use Euler's identity, e to the j theta equals cosine theta plus j sine theta. And it turns out that's, it's not just math in MRI, it's actually the physics of what we do. We're actually going to have, each spin is essentially going to be a phasor. Okay? And it can either go this way, or it can even go the other way in terms of once we're in the rotating frame of reference. All right? So having this picture of phasors turns out to be the most effective way of thinking about MRI. And just to remind you, sometimes unless you work with phasors a lot, this e to the j theta is deceptively simple and somewhat uncomfortable for people to look at. Just remember, the most important thing is this just tells you, all you have to worry about is the angle, theta. Okay, so that's just that you just need to know the angle of the phasor. All right. And by definition, theta is positive if we go counterclockwise. All right, so it's this way. And theta is negative if we go clockwise. Okay, so this is like a negative theta. This is a theta. That's theta. Okay, so Just remember that. So this, in this case, theta equals 0 is right along the x-axis, and this is theta minus pi over 2, theta pi over 2. So as long as you just remember that that argument theta is just the angle, you should be to get you fairly far. Okay, so now why are we talking about that? Well, here, once again, we've gotten rid of the bx and by components, so we just have this b naught component, right? And we already said before that this obviously just means dmz dt equals 0, so we don't need to worry about the mzt term, right? So we just have to look at the dmx dmy term. Okay, so just we need to look at, see, how are things working in the mx, my axes, all right? And so then we're going to define our magnetization. This is the key step. We're going to just keep track of our magnetization as a complex number, where its x component is the real part, and then we're going to assign my as the imaginary part. So because we have things that are just rotating around, it's useful to just think of them as phasors rotating around. Okay. And it turns out if we do that, then we get this very simple equation, okay, in terms of that complex number. And the solution is just a time varying phasor. M of t just equals its initial value or times e to the minus j gamma b naught of t, which just equals e to the minus j omega naught t, because remember omega naught equals gamma b naught, right? And this just has the form of m sub 0 e to the j theta of t, right? Where theta is equal to minus omega naught t. So all it is something that's saying my angle is just going to go like this, right? So theta, if you just remember that that's all that means, then, and that's going to rotate around like this, right? Because theta is just going to keep getting more and more negative, and it's just going to wrap around. So that's precession. So all we're saying is, we sort of gave you the physical understanding. Now we want to start developing the mathematical notation, so it's easier for us to explain what's going on. Okay, so any questions about that? That was just sort of a mathematical interlude. Okay, so now what we want to talk about is what happens to this magnetization. Okay, so ideally, if you had the magnetization and you tipped it away, then it would just precess. Okay? It would precess forever, right? If there was nothing to bring it back. But nothing in the world lasts forever, right? So eventually it's going to want to go back to its lowest energy state, right? Because you put energy into the system to tip it away, it's going to precess around, but essentially it's going to lose energy to its environment and go back to its lowest energy state. So that's what's known as free induction decay. Okay. We have this RF pulse. This is the B1 pulse. We put some energy in. So this is the excitation part. And then here we're going to listen. Okay. The magnetization is moving around, and we can listen to that magnetization. Okay. And the signal we receive looks like this. So you see it's decaying away. Right. So that's called free induction decay. And so one aspect you can think about it, this is the magnetization in the transverse plane. So transverse plane, we'll use that quite a bit. That's basically the MX, MY plane. Okay, so when we talk about transverse components, it's always MX, MY. When we talk about longitudinal, that's M sub Z. All right, so that's, you'll see those terms bandied around as well. So longitudinal is M sub Z. All right. Okay, so the next concept we want to sort of get you enough physics so you understand what's going on is relaxation. And this turns out to be really important because a lot of MR imaging is based on manipulating images based on the different relaxation properties of different tissues. Okay, so when you go for a clinical exam, there's going to be set sequences already that over time people have figured out, oh, if I have this, if I'm looking for like a tumor, I want to have it set up such that, you know, I see things that highlight tumors. Okay, so a lot of that's based on the fact that tumors might have different relaxation properties than healthy tissue. Okay, so that's what we make advantage of. So what we're going to do is we're going to do relaxation in 2 passes. Today, we're just going to give you the high level view of relaxation. Later on, a couple weeks from now, we're going to go deeper and tell you what causes relaxation. Okay, but for now, you're just going to be told this is what happens. All right. So there's 2 things. There's 2 types of relaxation. Okay. One affects the longitudinal component and the other affects the transverse components. Okay. So we're going to divide relaxation into 2 kinds. So there's a longitudinal relaxation, and that's basically determined by what's called the T1 time constant. Okay. And that's the return to equilibrium of m sub z. And then for mxy, there's going to call the T2 time constant, which is the return to equilibrium of mxy. Okay, so let's think about that. M sub z is going to go back to m0, right? That's its natural equilibrium state. What is the natural equilibrium state of the transverse? What is it going to try to go back to? 0, right? It's going to go away because remember, we had 0 transverse magnetization to start with. We had to tip it away to get some transverse components. So that's going to die away. So that's going to go to 0. So just also keeping that in mind is helpful. You know that longitudinal magnetization is always trying to go back to its equilibrium state. Transverse magnetization is always going to just die away. All right. Okay, so this is the governing dynamic equation for longitudinal relaxation. You'll look at this on your homework a little bit. It's mostly just sort of reviewing some basic first order linear differential equations. But we'll sort of go over the solutions here. And so really for the homework, you sort of can just plug and chug and just verify that these solutions work. Okay, so this is not a class on differential equations, but we do need to use some differential equations, right? Luckily, they're all just first order and fairly easy to know. And so you can sort of see here that this is, if we write this dmz dt equals minus mz t1 plus m naught t1. This is the term that's always trying to drive you back to m sub naught, right? Because that's a positive term, right? So you've got this competing thing where there is a decay away of the m sub z term, but this is driving you back to m sub naught. And so that's the picture you want to have in mind. No matter where you start off with, it's always going to try to get back to m naught. So this in case, this here is m sub 0, this line here. So here, after a 90-degree flip angle, right, we would have m sub z of 0 equals 0, right? That's the initial condition, right? Because we've tipped the magnetization all the way from here to here. So at this point, it has no longitudinal component. So mz 0 equals 0, right? So that's this picture here. I start off at 0, but then I exponentially recover back to m sub naught, and that's this equation here. Okay, so that's just exponential recovery to the magnetization, equilibrium magnetization. We'll talk a little bit more about why that happens later, but essentially it's sort of the magnetization being sort of giving up energy, sort of essentially giving up energy to the surroundings, okay? The useful thing is that different tissues have different T1 values. And so in this case, here on the x-axis, we plotted magnetic field strength in terms of Tesla. And here you can sort of see different tissues. So we've got like gray matter, white matter, which are different parts of your brain, muscle, kidney, liver, and fat. Okay. So basically, the key, which we'll take advantage of later on, is since different tissues have different T1s, we can actually start creating contrast by manipulating our sequence to make it so that different tissues have different brightness on the MRI image based on their T1. So if we do that, that would be called T1 contrast. And we'll talk later on how to make images with T1 contrast. Okay, the other thing we want to talk about is transverse relaxation. It's got a much simpler equation. It's basically just decaying away exponentially. Okay. And this one is basically due to the fact that the spins, you have lots of spins in your sample, right? Each spin is processing around, okay? And so each spin is essentially a magnet also that can affect basically the environment that this spin feels is due to all the spins around it. And so the spin-spin interaction is what causes this T2 essentially. And we'll get more into detail, but essentially this is the spin-to-spin interaction. And this causes all the spins to sort of dephase such that the net magnetization goes to 0. And also a useful fact is that T2 is always less than T1. It just turns out that whatever gives rise to T1 also contributes to T2, and therefore things will decay faster in the longitudinal plane than they recover in, sorry, they'll decay faster in the transverse plane, much faster typically than they recover in the longitudinal plane. So the solution is fairly simple. So for example, after a 90-degree excitation, the beginning value of the mxy equals 0 is just the magnetization, the equal magnetization, because we've tipped all the m sub 0 into the transverse plane. Okay. So then the solution is just mxy of t equals m naught e to the minus t over t2. So that's a very simple solution. And once again, the reason why we care about T2 is different tissues have different relaxation rates, different T2 values. Okay, so here we see gray matter and white matter here. And then CSF, which is cerebrospinal fluid, has a very long T2. So that's because it's almost like water. And so we'll want to make use of these sort of differences as we make our image. Okay, so as we alluded to before, this is basically when we tip our magnetization, the magnetization is made up of many spins. And so the random dephasing of the spins tends to cause this overall magnetization to go to 0. So that gives us what's called the Bloch equation, named after Felix Bloch. And all it's saying is we can write the equation of motion for magnetization in terms of 3 main things. Precession, which we talked about, which is just the magnetization going around. Transverse relaxation, which is the fact that it's going to decay in the transverse plane. And longitudinal relaxation, which is basically saying it's going to want to grow, the m sub z term wants to grow back. And it turns out you can write that in matrix form like that. And so you can start looking at different solutions. So for one thing, you can see that this DMC is decoupled from the rest, right? If we have B equals B0. In fact, it's just going to depend on the m sub z term. Okay. So this is the equation of motion. And I think you're asked to derive that this is actually the solution. So at least you know what the answer is. Okay. And so let's look at a couple, the 2 most common ways are either m sub z of 0 equals 0. Okay, so that's a very common thing. We're going to have a 90-degree flip angle. So we tip the magnetization all the way over. So the starting value of the longitudinal magnetization is 0. Okay. So in this case, it just grows back, as we said, to m sub naught. Okay. Later on, we're going to talk about inversion recovery, and that's actually also very popular. So this inversion recovery just means we're going to take the magnetization to put all the way over till it's pointing in the opposite direction. Okay. So here, m sub z of 0 equals minus m naught. Okay. And so what does that look like? We're going to start off at minus m naught. We're going to go back to m naught, and we're going to go like that. And look what happens as we go through. We cross 0. Okay. That turns out to be really important because that means that, let's say there's some tissue that I want to just erase from my image. Let's say there's a lot of let's say there's a lot of fluid that I just don't, it's sort of messing up my image and I want to just get rid of it. That means if I apply this inversion pulse and then I image at this time, essentially I've magnetically erased the contribution of that tissue. Okay. So inversion recovery turns out to be a real super important thing. Okay. All right, any questions? Okay. All right, so just to sum up, we've got, and then the transverse component, remember we're writing it as a complex number. And so it's going to follow an equation of motion that has both the precession term and the T2 decay term. Okay. And so I think there's actually a mistake here. Well, I'll check. I'll send a correction here. There is a J there, but there's something going on there. Okay, so it turns out that the solution has this simple form. It's m naught. This is just the precession term, right? Which we talked about before. Okay, that's the e to the minus j omega naught t, which is taking us around in the transverse plane. And this is the T2 decay term. And so what that means is I start off at some value here, and I just have this spiraling, I'm precession, and that's precessing, I'm just decaying away. Okay, so that's what the transverse component is doing. So this movie shows that sort of nicely. You can sort of see the magnetization is decaying away. So here you're seeing this decay of the transverse magnetization. And you sort of see here that T1 is longer. So even after this is decayed away to 0, this is still growing. So let me play that one more time just so you can sort of see it. So you sort of see this is rapidly decaying away. And even after this has gone to 0, this is still growing back. Okay? Because T1 is greater than T2. Question?
This is obviously the
Yes, this is, well, actually, this is not, this is still not in the rotating frame of reference simply because we have the omega naught, the spiraling. So that spiraling would go away if we were in the rotating frame of reference. In the rotating reference, it would just shrink like that. Yeah. Question?
So does the T1 and T2 relaxation always start at the same time as when we remove the B1?
Yes and no. Actually, even like, so for example, B1 field, we actually play out over time, right? Let's say we play out over some tau. Okay. It's actually, yeah, it actually begins right away. Like even as we're applying the B1, in fact, things are decaying while we're playing the B1. So everything is happening at the same time. If we could apply a delta function, you know, and just flip it right away, then we could imagine everything happens after that B1 field. But let's say we played in a limit, let's say you played a very long B1 field, which is done actually in practice, there are cases. Then people, when they design those things, they actually have to take into account the fact that as they're trying to flip the magnetization away, it's already decaying back. So there are tissues where actually, if your R pulse is too long, it's actually not effective because as you're trying to get it to do something, it's already decaying away.
But for MZ, it's you are referring to use the B1 then you will do it, right? But like for MXY, you will start
Everything is always trying to get back to its equilibrium state.
even for the
Yes. Yeah, exactly.
But when you're applying the B1 field, you're trying to increase the angle x-axis and spin the
Yes.
So in this process, you're basically just increasing this angle. How in this case, how is the MZ decay?
Oh, okay. So let me try to give you an analogy, right? Let's say I'm on that merry-go-round and you're trying to pull me off, right? And I'm always trying to stand back up, right? Okay. So basically, the longitudinal magnetization, I don't want to fall over, right? I want to stand back up, right? So if you do it very quickly, you'll be able to pull me over, right? But if you do it really slowly, as you're pulling me over, I'm always trying to stand up, right? So then it's not going to be as effective. So if I take too long to tip it over, then the T1 can sort of counteract that.
So it will like sort of like the spin angle will sort of like oscillate.
Well, in the limit, if you're too slow, you'll never even tip me over, right? Like let's say you go really slowly, then I can feel every pull you do, so I can always adjust to it, right? So let's say my time constant for returning back, like, you know, we're all very good at posture, right? So if someone pushes you very quickly, they can get you off balance, right? Because your time constant for retaining your posture is probably less than a second, right? I mean, we're all, and if you're an athlete, you're even better, right? You can get your posture back very quickly, right? You can return to your equilibrium state very quickly, right? So if someone tries to get you off balance very slowly, they're not even able to perturb you because you're always adjusting. So it's really the difference between the T1. If the T1 is very short, that means that they can recover very quickly. Okay. And so if you're too slow, you will never even be able to get them off equilibrium. All right. Okay. That's a good question. Anything else? Okay. So this is another picture. So longitudinal component recovers exponentially, and the transverse component persists and decays exponentially. So this is this picture here where typically things will decay fairly fast in the transverse component, and then as they're decaying this way, they're also recovering at the same time in the z direction. But even after they've decayed away most of it, there's still typically some z recovery that has to take place. Okay. Okay. So we've covered excitation, and then we've also done a little detour into relaxation because that's something that spins do. Just so you didn't get the picture that we excite. And that actually, the fact that things decay away actually is a very practical constraint on MRI. It means that typically, like if a T2 is only on the order of 50 milliseconds or 100 milliseconds for most tissue, and for bone, it can be even shorter, it can be less than a millisecond. That actually places a very strong engineering constraint and challenge. It means you've got to collect your data in that time. Okay, you've only got 100 milliseconds or maybe 50 milliseconds or maybe 10 milliseconds or maybe less than a millisecond to collect your data, okay? Because otherwise it's gone. Right? That MXY component is what is sort of that spinning around, and this spin spinning around and echoing and broadcasting to this coil is what we depend on. That's our signal. So if it's gone, then you have nothing to measure, and your signal. And in fact, if you measure too far out, if you're too slow, you just get a black image. Okay. So that's why it's actually quite important to keep in mind, and so that's why people are always sort of keeping in mind that, you know, it's not like you have the luxury of just spending lots of time collecting your data. You got to go fast. Okay. Because if you're too slow, there's nothing. Okay. Yes.
Change from like constant magnetic field to the pulse point, would that keep, I guess, the sort of the precision longer?
Yeah, I mean, there are different tricks you can play. I mean, you can try to keep tipping it back in. And in fact, one of the sequences we'll get into later in the course is something where you plot, you just always tipping the magnetization. And so, for example, that is a trick that people use. If you go in an MR exam, typically the first thing that they have to do is what's called either a localizer or a scout. They just want a very quick image that can be done in like 10 seconds, just to say where is the body or where's the head. So then they can then prescribe the image based on that. That's done with these sort of pulses that just sort of go very quickly, where you actually say, I don't need much signal, but I just want to go fast. So there are these trade-offs you can make. Yeah. Okay, so the next thing we're going to talk about in the last, I guess, 20 minutes, yeah, is encoding. So we're going to set you up to sort of start thinking about encoding, and then we'll finish up encoding next time. And then I don't think we'll get to integration today, but we'll see. Okay, so just to remind you, the encoding part is done by these MRI gradients, and there's typically a X, a Y, and a Z coil. Okay. And in this class, we're going to just talk about linear gradients. People are working on nonlinear gradients, but that's sort of beyond the scope of this class, although something that if you're looking for a project, you know, there are nonlinear gradients. You could do it with nonlinear gradients. It just makes all the math much more complicated, but that's something, if you're so inclined, that might be interesting to look at. Okay, so just to remind you, what we're talking about is that the key is always remember that spins persist at the Larmor frequency. And the key is it's the local magnetic field which determines that. So if everything is uniform, then BZ equals B naught, right? So all the spins persist at the same frequency. Right? So we had all these spins, think each spin has a little radio station, they're all broadcasting at the same frequency. Okay. So the key is we don't want that. We want them to broadcast at different frequencies. Okay. So the key is we're going to add a spatial variation to B sub z such that now B sub z is a function of x, y, and z, and it's equal to the main field plus some delta B of z that we've added. And that's what the gradients do. So the x gradient causes the variation in the x direction, the y gradient causes the variation in the y direction, and the z in the z direction. Okay. Therefore, spins at different locations can now process at different frequencies. That's going to be the key. That was the key insight that led to MRI being used as an imaging modality. So here's another way of looking at this. So this is plotting the delta BZ. And in this case, we're using a GX gradient. So GX means gradient in the x direction. And so the delta BC is just GX times X. So we're at an isocenter. So isocenter is here. This is what we call isocenter. Okay, that's a term that's used. Basically, that's where the gradient field's always zero. So when people talk about isocenter, so typically in MR exam, the first thing that we do is we put the subject in and then we hit a button that just says advance to isocenter. So boom, it puts the subject in. So the middle of the volume we care about is at isocenter where there's zero gradient. Okay, so the gradient fields are all set up that there's zero at this one location. That's isocenter. So spins at isocenter process at gamma B naught. Spins here in the positive x direction process at gamma B naught plus gamma times GXX because we've got this additional B field. So they're going to go faster, right? And spins here at a negative x direction spin at gamma B naught minus gamma GXX. So they're going to go slower. And that's the key to MRI is just making spins go at different precession frequencies. Okay, so here's an example here of, let's say this is the x direction. So you can sort of see here at the isos, and here we're going to assume things are in the rotating frame. Okay, so in the rotating frame, even though the things at the isocenter are processing at gamma B naught, we're going to assume that they're, from the point of view of the rotating frame, they're not rotating at all. Okay, so here you can sort of see here these spins are going faster in the clockwise direction, right? These must be in a stronger magnetic field. Okay. And these spins are going relatively slower, okay, because they're going sort of counterclockwise. And so this would be, you know, plus delta B, and this would be minus delta B, right? Okay, so you can sort of, even just by looking at these spins, how fast they're processing. This is processing faster than this one, right? And so it's the relative rate of precession that matters, and these are not processing at all, so these are at isocenter. Okay. So here we apply the gradient in the x direction. Okay. Here we apply the gradient in the y direction. So let's see here, the gradient is stronger here, right? Because these spins are going faster in the clockwise direction. Right. So remember we had e to the minus j omega t is my precession, right? So the bigger omega is, the faster these are processing. And this is processing faster than this because with a gradient, this is in a stronger field than this, right? And then here, these are processing slower. So they're looking, reference to isocenter, they're moving in a counterclockwise direction. Okay. So it turns out that this, for your homeworks and things, this negative sign turned out to be fairly important, okay? Because it's saying that faster is faster in the clockwise direction. And then here it's just showing that we can apply gradient both in the x direction and the y direction. So now we have to look at diagonal lines, right? So here, this guy is processing the fastest, right? So this is in the strongest field. This line here is in a less strong field. This is in a less strong field, and so on and so forth. All right. Okay. And I think I haven't checked this link, but if this link is not working and you want to look at it, just let me know and I'll try to find something similar. Okay, so let's actually skip this example problem for in the interest of time and just give you sort of an overview of, and we'll get back to that next time. But I want to just leave you with sort of an overview of sort of how MRI imaging could work. And once again, we're going to use the rotating frame of reference. And so here, imagine this is a spin at the isocenter, so it's rotating in the clockwise direction. At the isocenter, we assume it's not rotating at all. Okay? So for example, we're going to draw the MXY components. It's going to just be spin at isocenter is going to just always point in that direction. Erwin Hahn was a physicist at UC Berkeley who died a few years ago, I think. And he had this nice quote I like, that there's nothing that nuclear spins will not do for you as long as you treat them as human beings. So pre-COVID, we tended to do these as in class. And if the class was smaller, I'd probably still do that. If it wasn't on Zoom, I'd still do this. But once we went to COVID Zoom, I came up with this sort of example, which is not as good. I'd rather still do it in person. But I'll tell you what we would have done. So if I was doing this in person, I would have had 5 of you come up to the front of the class and be the spins, okay? And just sort of imagine, you know, so don't get nervous, we're not gonna do it, but typically there's a moment where people are like, oh, I don't wanna go up, or usually there'll be 1 or 2 people who are really excited and run up to the class, and then the 3 remaining spins I have to like, wait a minute to do. But I would actually have you all line up facing that wall there. Okay, so just imagine that this could be you, okay? You're just lined up facing the wall, okay? So this is at time equals 0, okay? And so the first thing I do is I just have everyone line up, okay? And then I say, imagine you're in a B0 field pointing up, okay? And the first thing I have them do is I imagine them, and this is, everyone in the audience doesn't really have to do much work. The spins actually have to do quite a lot of work. So I tell them that when I say start, I want you to start processing, okay? So imagine you're lined up. These people are lined up in the room and they're all facing that direction. And at time equal, and the B0 field's this way, right? And I say process. So what should these spins do? Yeah, they should rotate in a clockwise fashion, right? And so that typically most people will do that. But one thing that they do is sometimes they're not all in sync, right? They might be rotating at different frequencies, right? So I say, well, that's not quite correct. So so let's say I had some people a group of people and they're rotating at slightly different rates. How would they correct themselves? Right, and what are they trying to achieve? What are they trying to be? Should they basically, if they're going at different rates, should they stay at different rates or should they try to go to the same rate? Yeah, so basically, if they're in a uniform field, they all want to go at the same rate. Okay. So the next thing I do is I say, assume that there's a gradient field, okay, in this direction, all right? So that the field, so for example, let's say there's a gradient, and so let's say this is the x direction, and then there's some gradient field where this is the isocenter, and the fields get stronger as you go in that direction. Right? So that's applying like an x gradient. Okay. So what I would tell the person in front is, you are in the strongest field, so you're going to process faster at everything. So I'll tell this person to go plus 180 degrees at every step. Okay. And then the next person over is processing less, so it's only going to go plus 90 degrees. But when I say this is clockwise, this is always clockwise. Okay, so 90 degrees, 180 degrees clockwise, or 90 degrees clockwise. Okay. And this person has the easiest job of all because it's an isocenter. So it just stays there for the entire thing. And now we're in the rotating frame of reference. Okay. Oh, sorry, I forgot to say, typically the thing I do is I have them all process, and then I'll say, now you assume you're in the rotating frame of reference. Okay. And you're in a uniform field, and now process. Now, so what should they do? So imagine you're here, you're lined up here, and you're told there's a B0 field here, and you're in a rotating frame of reference. Now process. So what should you do? Sorry, go ahead. Do not do anything. Yeah. So typically you'll see people like want to move, but then they'll say the other person's not moving. So typically people get it. Okay. So that's the key. And so this person here at the isocenter is not going to move at all. This person here, who's in a weaker field, is going to go 90 degrees counterclockwise at every step. And this person here is going to go 180 degree counterclockwise at every step. So essentially we imagine at time equals 0, everything is lined up, and then we apply the gradient and we just see what happens over time. And so this is the main picture I want to leave with you today is what would happen if we did that experiment. So let's do the first step. Okay, so this person went 180 degrees clockwise, right? This person went 90 degrees clockwise. This person went 90 degrees counterclockwise. And this person went 180 counterclockwise. So you see there's a spatial variation in their orientations, right? And so let's call this distance between them delta x. Okay. What is this? What is the period of that spatial variation? How far do I have to go before two spins have the same orientation? Sorry, go ahead. 4, yeah. So the period here is equal to 4 delta x. Okay, or we could say that the spatial frequency is 1 over 4 delta x, right? Okay. Next step. This guy has gone another 180 degrees, so he's pointing back here. This guy's gone another 90 degrees, so he's pointing this way. This person is still the same direction. This person has gone another 90 degrees counterclockwise, so now it's facing this way. And this person has gone another 180 degrees counterclockwise, so it's sort of gone from here to there. So now what is the spatial period of the variations? 2, right? So now I'm at 2 delta x. So I'm at kx equals 1 over 2 delta x. Right? Okay. Now we continue the experiment. This person has flipped from here to here. This person has kept going, so now it's facing away from us. This person is still in the same direction. This person is now facing towards us. This person is facing that way. So now what is the spatial period? Back to 4, right? Okay, so these two have the same spatial period, right? What's different about these two rows? So going from here to here, what's different about going from here to here versus going from here to here? The orientation is different, right? So this is essentially like what you did in your homework 4, right? The orientation between positive and negative frequencies is different, right? The way the phasors go, it's either this way or this way, right? So this is essentially what we're seeing in MRI. That's why we can have positive and negative frequencies, because even though the period is the same, the way in which they do that, they could have either gone one way or the other way. Okay? So this is what we mean by the difference between positive versus negative frequencies. Okay. And then the last thing is we do one more step, at least in this example, then it'll end up here. So now what is the spatial period here? It's 1, right? But in this case, is there any spatial variation at all? So where will we say that this is in terms of kx? What frequency is this? 0, right? So this is what we mean by 0 frequency. So really there's no period to talk about, right? There's period is sort of undefined because there's no spatial variation. Okay. So this is sort of basically what we're doing with spins. As you can sort of see, these are spins and we just play them out in the presence of a gradient. Now this is a very simplified example, but the point I want to get across is we were able to get different periods of spatial variation, right? And essentially these are going to turn out to be our Fourier basis functions. Okay. So this is just drawing that from a top plan view, same idea. You can sort of see that, you know, this is this period, this period, this period. So now in the last 4 minutes, basically I want to just leave you and with an idea of how we're going to go from that picture to now getting to this. Remember, this is just our expression for a Fourier transform, right? It says, if you want the Fourier transform of some function g of x, multiplied by some phasor that is e to the minus j 2 pi kx x, and then integrate, and that will give you the value. Now, as we said before, this just means, this is just of the form e to the j theta. So this means I just want something that where the angle varies as minus 2 pi kxx. Okay. And so, for example, if I have kx equals to 1, that means my period is also equal to 1, right? Okay, so here I'm looking at x equals 0, x equals 1/4, x equals 1/2, x equals 3/4. So this just means that the way to think about this phasor is that at x equals 0, 2 pi kx just equals 0, right? So this has 0 phase, right? K equals 0. If I go to x equals 1/4, 2 pi kx equals pi over 2. But since I want minus of that, then I get theta equals minus pi over 2. Okay. And then at x equals 1/2, I get it's theta equals pi. And then x equals 3/4, I get x equals pi over 2. All right. So this is a case where I had kx equals 1, which is greater than 0. So this is a positive frequency. So that sort of shows the relative variation in the spin phase as I move in the x direction. So we can now think about things like this. What we want to do is sort of start developing an intuition for what different spatial frequencies look like. So this is kx equals 0. Right? So this looks exactly like what we had in our example. All the spins have 0 phase. Right? Now we're looking at things, we're going to vary things in kx now. The next thing we're going to do is now we're going to assume that kx equals 1/8 delta kx. That means the period is equal to 4 delta x. Okay. That's sort of 8 delta x. Right? So period is just 1 over the spatial frequency. So that if you look at this, this is pointing up and this is pointing down, right? So half a period is 4 delta x, right? So one period is 8 delta x. Okay. So if I look at this, here's the isocenter, right? This is always at 0 phase. And then I'm going, these are going to be more negative. And the phase increases as I move in this direction. And here, less, I'm moving in the counterclockwise direction. This is very similar to what we did in our example, except here I've taken smaller step sizes, right? Instead of, yes, go ahead. Kx equals 0 because that means there's 0 spatial frequency, right? So for example, if I have e to the minus j 2 pi kxx, right? This term is equal to 0 when kx equals 0, right? For any x. So therefore theta is equal to 0 for any x. Yeah. Okay. The period is undefined though, right? Because 1 over kx is not defined. But kx equals 0 is well defined. All right. And here I've got kx equals 2/8 delta x, which is also equal to 1/4 delta x. So the period here is equal to 4 delta x. And in fact, you can sort of see going from here to here is that 4 delta x we saw in our example. So e to the minus j 2 pi 2/8 delta kx looks just like this. And so all I'm just showing you here is the spin orientations that we came up with in our example are just essentially physical manifestations or examples of these complex phasors. Yes.
So I guess another way that could be is like kx is like modifying the resolution frequency.
Yes, that's
So
right.
as kx increases, we have more separation between frequencies based on x.
As kx increases, then the spatial variations that you can measure decrease. Yeah, so higher kx means smaller period. So the spins are going to change much faster. And what we're going to see next time is we're going to review what high kx and low kx means. So high kx is like outer k space. That's going to give you the details. Low kx is inner k space. That's going to give you the overall structure.
So what you're actually going to do is instead of defining one kx, you're going to sweep across a
Yes,
certain range of them.
exactly. We're going to have to acquire data in kx. So 1 kx is not enough. We have to have a lot of kx's. Yeah. So every kx sort of picks up a different sort of spatial frequency. But to make our image, as we'll see next time, we have to get information from all those different spatial frequencies. Great. Okay, so we're at the end of our time. So let's end here. And then if there's questions, feel free to come up and ask, or you can ask questions on Zoom. Okay. And we'll see you on Wednesday. And I will post the next pre-quiz later today.